Dear colleagues, it is my pleasure to open the plenary session of our conference. Our first talk will be presented by Professor Petia Georgieva. Professor Petia Georgieva is professor in machine learning with the Department of Electronics, Telecommunications and Informatics, University of Aveiro, Portugal. A senior researcher with the Institute of Electronics Engineering and Telematics of Aveiro, Portugal, and a collaborator member of the Institute of Telecommunications Aveiro. Previously, she had academic positions with the University of Porto, research visiting positions with the Rowan University USA, Carnegie Mellon University USA, University of Lancaster, UK, and the Bulgarian Academy of Sciences in Sofia. Her interests are in the area of machine learning, deep learning, data mining, signal processing, and control. Her work involves development of novel techniques for high-dimensional problems, including neurocomputing, brain-computer interfaces, image processing, and so on. I forgot to mention that Professor Petia Georgieva has graduated from the Technical University of Sofia, formerly VEMI Sofia. Professor Georgieva is a senior member of IEEE and senior member of International Neural Network Society. She was the head of Signal Processing Lab in IET, a member of the Executive Committee of the European Neural Network Society, a member of the IEEE working groups. Since 2010, she has been an European Union expert and evaluator for several research grants and running projects, including some programs of the European Commission. After these introducing remarks, it is my pleasure to announce the topic which Professor Georgieva will present, namely Explainable Artificial Intelligence in Healthcare Applications, a systematic review.
The organizers for inviting me to give this talk. Thank you, Vlado. It's really a great honor for me to be here and to give this talk after many years being part of this department, being part of this faculty. Here I see faces of my professors, faces of my colleagues, and I'm really very emotional, I must say. What I wanted to talk to you today is a short overview of my work. Of course, it's always related, the work of professors in the university is always related with the brilliant students. So this is a master student of mine, Beatriz Costa. And the whole journey that we had with her, now she is my PhD student, to convince medical doctors that what we are doing makes sense, that we can help them. I just would like to show you the whole path, I mean the whole stages of starting from images and then trying to explain to doctors what is exactly showing this algorithm, these fancy algorithms that nowadays are quite popular and that sometimes are scaring because the medical doctors don't understand what we are doing exactly. So, and the problems are not only with the explanation, but the problems are also with a lot of many other steps, challenging steps that I would like to share with you. So what you see here is actually these two areas of artificial intelligence. We have this classical machine learning approach and this deep learning approach. And in the past, before the era of deep learning, the images were processed by standard algorithms, machine learning algorithms. What you see here is just one neural network. So the image has been destroyed, transformed into a very long vector. And this vector, these pixels, are the input of the classical neural network or some other classifier, because from a machine learning point of view, from AI point of view, the problem here is how to classify the image as the image of a healthy person or image of some illness. So this is in fact the classification. And after that, during the era of convolutional, the deep learning, I don't enter into too many details. Probably for some of you, this is too basic introduction. For others, it's not quite clear. We all come from different backgrounds. But the deep learning algorithms, particularly the convolutional neural network, they don't destroy the image, so they process the image the way it is. And then through those layers, during the so-called convolutional layers, are extracted the features, the most important features based on which the algorithms needs to take a decision. Because when we speak about AI, artificial intelligence, or the major goal is to take decision instead of us, do some job instead of us. So, and here the idea is that through those layers are extracted the features. And at the end of the convolutional layers, there are other layers where actually the decision is taken. So here is actually the classifier. So the learning during this process, so the image is processed the way it is, 2D or 3D, depending on if this is an RGB image or it's a black and white image. And at the end has to take decision how? Based on labeled images. So we need to provide the algorithm with labeled data. And then during this training of the algorithm, so the error between what the model predicts and what is the real truth, because we know if this image belongs to an ill person or not. During this training, there is something that we call backpropagation. The training of the model is done by backpropagating the error. So this backpropagation is a very complex process that I just mentioned here because I will need it later on when we speak about explainability. So the training is something what you see here. Forward processing of the image data, transforming, extracting the features based on some mathematical transformation, and then going backward propagation in order to train the parameters of the model so that at the end of many images, the algorithm learns to distinguish between, for example, these two types of images. So here is, for example, we worked with skin cancer diagnosis problems, where we need to have a lot of images given by the doctors, images that are previously labeled by the doctors, if this is a cancer type of skin image or not. And then we apply those complex multi-layer algorithms in order to make the decision. So then we worked also with some, in ophthalmology, we worked with some images taken from, in order to identify diabetic retinopathy problems. So again, we had medical doctors to previously label the images as having healthy or diseased images, and then these were also processed by some algorithms, and I'm speaking a minute about particular algorithms to do this. So when we speak about histopathology, the things are a little bit different. In the previous cases, these are the complete image. We use this image the way it is. Probably we can resize it somehow, but this is the complete image. In histopathology, the problem is different. And these are huge images, something like 100,000 by 100,000 pixels, so it's not possible to work with the complete image, and in fact, it doesn't make sense. The complete image, usually the medical doctors are going to manually define what are the areas with where, for example, the cancer spread, in which areas of this whole image. So we take from this big image, we need to extract only patches, small patches, and this part is already done by us after the medical doctors has identified the area, manually identified the area. We take the patches, and if in this patch there are many pixels that belongs to the infected area, we label it as a patch that belongs to affected part of the histopathology image or not. I mean, this is later on by us labeled based on this manually defined areas of this huge image. And again, after we extract all those small patches, already we consider them the same way as images, and they are again preserved by the same algorithms. I mean, the idea is that we use the same algorithms, we just need to formulate the problem in the terminology of machine learning classifier. So then, this is the X-ray images. This is a very popular data set. We took it from Kaggle. I mean, a lot of the work we have done before going to contact the medical doctors, I usually taken publicly available data, training our algorithms to gain some experience, and after that we can contact them and propose to solve their particular problem using our pre-trained algorithms. So here the problem is a little bit more complex because X-ray is a very typical type of images, and based on the X-ray it can be identified much more a big variety of pathologies. So here are shown 14 different pathologies, and for each one of them we need to identify, our model need to identify if this pathology is present or not from a big number of different pathologies. So those that are going to participate tomorrow in the workshop, so I prepared, it's going to be a practical work using Python, trying to identify all those pathologies. I prepared the lab work. First I will give you an overview of deep learning algorithms and compare the machine learning with deep learning. Then for those that would like the challenge, so please bring your computers. I have already starting code in Python using some libraries, so you can try yourself with my help to do this and see practically how does it happen. This is a lab work that I usually give to my PhD students during the classes. Okay? So here the big problem actually, not only with this data, but the big problem in general with the medical images is that these are unbalanced data. I mean, we have plenty of healthy images and much less number of unhealthy. And here you see, for example, on this figure, you see this yellow color means healthy, so negative for a certain, for each one of those 14 pathologies. And you see in the blue color shows how many images we have from the pathology, with a certain pathology. And so from one side we have much less number of images with pathology than not pathology from one side, and from the other side we have, between those with pathology, we have much more from some pathology, much less from the other pathologies. So it's highly unbalanced data. If we work with such data, we cannot extract too much information. Our model classifier means that is going to be biased towards the healthy images or towards only some of the pathologies. So the first step is to balance the data. So what are the ways to do this? Here you see the simplest ways, I mean just intuitive ways, undersampling and oversampling. I mean oversampling, undersampling is if I have too many healthy images, take only some of them, a part of them. Or oversampling, if I have only few that are related with some pathology, so double them, or triple them. So this is a way to balance the data. Very naive, but it works, believe me. Another way, much more fancy, much more advanced way is data augmentation. Now it's a huge area of generating artificially data, making some photographic tricks like rotation, like horizontal flips, adding some additional, images in the computer represented if they have been encoded with 8 bits. These are going to be numbers from 0 to 255. And if we change those numbers, we can increase the contrast, we can increase the brightness. Really photographic tricks. And there are no rules how to do this. We usually do this in a completely random way. I will apply a number of different tricks, photographic tricks, in order to get just change data, somehow change data. And other more fancy that is going to be done tomorrow during the work workshop is to apply, because when learning this machine learning, training means optimization problem. When we train the model, we actually optimize some cost function or loss function, and this cost function is related with how the model predict if this is a illness or not, and the real label. We know the ground truth. So based on this discrepancy, we build some, I don't enter into too many details, cross-entropy functions, some cost function where we have two terms. If we do binary classification, healthy, unhealthy images, we have one part with positive examples or with examples with the pathology, and another part of this cost function with respect to healthy images. So in these two parts, we weight them by some weights that depends on the quantity of healthy and unhealthy images. So it means that in this way I will give, or my algorithm will get more, will take with more importance the errors done with the less representative class. We will give more importance to this class that has less representation, which makes sense. Okay? So this is another way to solve the problem with unbalanced data. So after we apply this, I just show you here that initially this is the relation between the proportion of the data with respect to healthy and unhealthy, and after we apply those weightings, we give more importance of the few images that belongs to the unhealthy images, and we equalize the importance of the two types of data. And this is quite useful for the algorithm not to learn more, to be biased towards one of the classes. Another problem that we faced was initially, guys that work in machine learning algorithms, they know very well we need at least to divide the data into training, validation, and test data in order to train our algorithms. And we usually do this randomly. We think that this is fine, this is statistically more relevant to divide this into these three sets, but if we do this, particularly with patient data, it can happen that the same patient, the data of the same patient goes in three different subsets. For example, this patient 20 can become part of training, validation, and test data, and the medical doctors didn't like this. They told us, no way. I would like to have all data, so then this is done the way they want it. Split by patient. So they want to have one patient, all images, all data related to one patient in one of the sets, and we have then the other patients into the sets. Because, having these patients, they explained us why they want this. Having these patients, they want to make a cluster of behavior of one patient, and then based on this cluster, then looking at the other images, probably say, wow, this patient seems similar to the cluster of the other patient, so I will assign it probably the same pathology. So they want to do this, to have this the divisions of those who are starting to work with medical doctors. Ask them, and you would like to apply these algorithms, ask them how they want to have the data divided. It's very important, the way we split the data and train our algorithms. Right? So the huge problem, another problem that we had is labeling. Labeling, because it's so subjective. Labeling is done by medical doctors. And usually one doctor may have a disagreement with another one. So in this case, the best way is at least to have like an odd number of medical doctors, so that you take the majority of the votes. But it's always better if you can just make, and they prefer this, though it's more expensive, they prefer to just make more exams. So in this case, for example, with the X-rays image, they want also to make the computer tomography to be the second opinion and then take the final decision. Or in the case of the skin cancer, we had to actually work also with histopathology images. That is how we came to this type of images. We were happy to work with the skin images. They're much easier to work, but then if you have a second type of information, you have to adjust your algorithms and to make some changes. But again, this is usually the better solution, to have more exams than voting or using just the opinion of one medical doctor. But it's a challenge. Even if we have all this done, we are going to end up with relatively small amount of labeled images. It's a huge problem to have enough data to train all these deep models. And I will come to the deep model on the next slide. So this is the problem that has to be also solved, to have credible labels, data with credible labels. And then come the last moment, that we need to actually normalize the data. So usually the standard way to normalize the data, the images, again, if the intensity is some numbers between 0 and 255, just dividing by 255, we got data between 0 and 1, and these are our original images. Between 0 and 1. The distribution of pixels of the images are just between 0 and 1. This is the standard normalization. But we found, not only we, of course other people are working in this area, and we consult their papers, we found that normalization by taking the mean, making the mean, computing the mean and standard deviation, and then subtracting the mean from each one of the pixels, and dividing by the standard deviation, so that all data, all these pixels are already pixels with mean equal to 0 and standard deviation equal to 1, works better. So this is actually, what you see here is the distribution of the pixels of the normalized images of those X-ray images that you will work tomorrow. Okay? And so finally, after we do this normalization, we are ready to go. We are ready to plug it into the model and to train it. And this is actually one of the models. I mean, we like it because it has been done. It has been used by previous researchers, and the results are quite promising. This is the so-called dense net. So what you see, dense net is a very deep neural network with, I will show you then what we work with. We work with 121 layers, but they are even bigger. So what you see here is just one block of this network, just a block. This is not the complete neural network, this is just one block, just to illustrate you. This dense net is, in this deep neural networks, the information flows from one layer to another, to third, and so on, sequentially. But in the dense net, we have connection like fast track connection or fast link connection between, for example, the first layer in this block is connected with all next layers directly. I mean, and the reason for doing this is one huge problem in deep learning known as vanishing gradients. So in order to overcome the problem with vanishing gradients, I think I tried to illustrate here the problem with vanishing gradient. So as I told you, when we train the neural network, we get only the error at the end. At the end, the neural network tells us what is the pathology, or is there a pathology or not. And we compare with the label and we get the error. And then this error has to be propagated, back propagated, and I don't know where to write. And then there are a lot of parameters in the model that has to be tuned based on the so-called gradient descent algorithm. So gradient descent algorithm, in order to update the parameters of the model, it's done by some updating term that is related with the gradient of the error with respect to this parameter that we want to update. So, but if you have huge amount of layers, so this gradient start vanishing, it means it goes to zero. You see here in the 10th layer, the gradient norm is some number, but for the first layer, so it's a very long model, for the first layers this gradient will go to zero. Once the gradient goes to zero, it means there is no adaptation of the parameters, it means no learning, so the model stopped learning. So it's the problem, and you know, many of the things that I tell you here are, I mean, some people call all these models empirical, because many of the things are, we tried it, it worked. I mean, there is no theory, there is no big theory there. There are a lot of concept, mathematical concepts like the optimization algorithms, but particularly the choice of a huge number of hyperparameters in these models is very empirical. So in this case, they have noticed that if we add, I mean, I have this on the next slide. If we add this fast links from the previous layer later on to the next layers, the information that otherwise will be lost because of the vanishing gradient, or the lack of learning because of the vanishing gradient, it will be compensated by this fast track. So this is the underlying idea of dense net, and it works. You test it, it works. So this is the architecture. Here you see, probably I don't need to go into too many details, because each one of those blocks consists of some batch normalization. Then it comes a very important function, real mathematical function, because all these neural networks are based on some mathematical functions, sigmoid, hyperbolic sigmoid. But in the deep learning algorithms, the major functions that are used are the so-called ReLU, rectified linear. So rectified linear is nothing big deal. It's just a function that if the input of this function is negative number, the output is zero. And if the input is a positive number, the output is going to be either the same number or is going to be augmented the same number. So it will be bigger positive number. So it's a very simple, mathematical functions, activation functions known, or neurons, also different terms used. And the idea is actually to the whole idea of neural networks, they call this imitating the way our brain works, imitating, but a very loose imitation, I must say. Nothing related, you don't imagine that all these neural networks try to imitate the way we think, for example, at the cognitive level. No, it's just the way how in the biological neurons, after the pressure, so you see the cell, after the pressure on this cell, these are, for example, blood pressure goes above a certain threshold, the neuron fires. So this is the same idea. This ReLU is going to fire to augment some positive input. And I will explain why I spoke that many details, because ReLU is a key element in the explainability in the algorithm that I will explain. So the ReLU is an important function. Then there are other elements that drop out, but I will not speak about those details. So here you see the DenseNet family. So you see DenseNet 121 that was invented in 2016, then one DenseNet 169, so these numbers means number of layers. Then 201, then 264. We trained this one because of the lack of enough data and because of the lack of enough computational resources, because, if you would like to train all those monsters from scratch, you need to go to Google, and this is what happened. We went to Google and we asked them for computational power. And they gave us, but they asked us to pay. Since we are a university, we pay less, but we still pay. They make a lot of money just because we are going to use their computational resources. If we want to train our networks, but then they propose us even better solution. Don't train your models, take our pre-trained models, use transfer learning. So they are really defining the rules of the game, and we just follow them. Okay? So now I come to the this explainability part. After we all this training and learning of the model is independent of explainability. I will show you that in the next slide that there is this in parallel. We do the training, we use the models to predict, and then we add an extra line to explain the doctors what we are doing. So a little bit of math, otherwise cannot explain the algorithm. So this is the term global average pooling. So in the layers, in this mathematical layers, so each one of these elements is one neuron, one real neuron. So at the end, at the output of each one of the layers, we have this 3D volume that is known as feature map. So this is not anymore my image. The image was at the input, and after it has been processed by these neurons, at the output are some numbers. Okay? Numbers, zeros or positive numbers. And this is a 3D. So this is the height, the width, and the depthness or the channels, number of the channels. So, and usually in these deep algorithms we have what we call reduction of the dimension of this volume. Why? Because we would like to reduce the number of the trainable parameters. So the standard reduction of this volume is now, for example, to take one small patch 2 by 2 patch from this volume and to choose the so-called max pooling, to choose either the max value from those 4 or choose the mean value of these 4, and this is my output. And this global average pooling is very aggressive. I'm not going to choose just a small patch, but I'm going to choose the whole one-dimensional matrix, this one, and choose mean value or max value, usually the mean value. In this global average pooling is the mean value. So we end up, after we apply this global average pooling, we end up with such architecture, much smaller, with some mean values. So the goal is to find where in the original image, which were the pixels that provoked the highest firing in the neurons. This is the idea, to see which were the pixels in the image where that provoked this highest interest. That means there is something important in this part of the image that, based on this important thing in this part of the image, the algorithm took a decision. So, so this is actually the first step in the algorithm. Then, here a little bit, don't pay too much attention of those maths, but these are explaining what is the forward path, what is the backward part, what is the deconvolution part. I mean, all are some rules. These are some rules. How to propagate this back propagation, how to be done. I told you at the beginning that there is a need to back propagate the error so that we update the parameters. And so this back propagation is done following some rules. And here you see the rules. And the rules are propagate in the back only what is important. And what is important has to be a positive number. The negative numbers are not important. Don't consider them. It's something like that. So at the end of the day, we started with forward path with a lot of positive, negative numbers, And here at the end we have everything full of zero and only a few positive numbers. So these positive numbers are the important parts. So from them we will try to see what are the pixels that provoke this biggest number in this back-propagated, following strict number of strict rules that you don't need to memorize. Okay? So then this is already applied to the to do the job, to show in the image which is the most important part that based on which the algorithm took a decision. And you see here now, starting from the original image, going through a number of convolutional layers, extracting the features, and then if it is a normal neural network, we need to have the classification number. We take this out, and at the end of this parts of the convolutional layers where we are extracting the features, we do this global average pooling. We end up with this one-dimensional already vector array, and each one of the outputs, I mean, here what you see on this slide is the case when we don't have only two classes, but we have more than two classes, like in the multi-pathology images. That each one of these outputs is related with one of the classes. So here is, if this is a terrier or this is a child, I mean different objects to be identified. I just did not find a better image with medical images to illustrate you the idea of the class activation mapping. But after the neural network has learned its parameters, these weights, each of them multiply the image in order to create this low class activation map, and should show us which were the pixels in the original images that actually, based on which this class was defined. If this is defining this dog, the terrier, so it's going to be shown that this part of the image, where is the terrier, was important to define that this is the terrier. They need to see in which part each one of the classes was discovered. Okay. So finally you see all these together already with the original input, the convolutional neural network. It creates its feature map. Here it would be actually the part of the classification, and here are the different classes, I mean the output with the different classes. But then simultaneously, before the classification part, here at the features, we applied our global averaging, the GradCam approach, global averaging pooling, and then got the map related with applying ReLU, when we applied these rules that I told you for backpropagation, so that we find what is the area. So there is even more fancy algorithm that is here, this GradCam, because it's going to now combine from one side this CAM algorithm that shows us just the area, what is the area showing with a different color that is responsible for this decision, for the class decision. But they goes to even more detailed, so they don't want to show us the whole area. The doctors don't find this quite useful, but they would like to go into say each one of the pixels, the importance of each one of the pixels. Here, for example, some of the pixels have more importance in this area than other pixels. But it's not that quite informative from a medical point of view. The doctors are happy if they just see this part, and if I speak about cancer and not cancer images, and if the algorithms guides them and shows area where they also would look with their expertise, and it coincides, then they believe the algorithm. I mean, if the algorithm is showing different positions, they start doubting if this is actually, this makes sense. Maybe if I have more. No, that's my presentation. I don't know if I went beyond my time.
You have more time.
Actually, I just wanted to show you that Cambada Robo Soccer team, that is the team of my department in University of Aveiro. In 2008 we were the world champion of middle-sized RoboCup. In 2018 we were the second place. And last year we were the second place, but unfortunately I must tell you that everything now is done at a simulation level. I mean, a lot of those competitions, COVID was disasters for this competition. I don't know if we are going to now to recover, but last year we had a competition, it was just the simulation level. Yeah, one more slide. This is the Aveiro. Aveiro is considered as the Portuguese Venice. It's a very beautiful city. Portugal is famous with architecture. So there is no Nobel Prize for architecture, but there is a Blitzker Award that is equivalent of Nobel Prize for architecture. And Álvaro Siza Vieira and Eduardo Souto da Moura are two Portuguese architects that got those prizes. They designed the campus. This is the wall of the library, and this is part of famous almanacs of contemporary architecture. So come to Porto, to Aveiro.
Okay, I'm opening now the panel for questions. Do you have questions?
What do you think about the quality of the recognized image?
The quality.
Using the deep learning.
It depends. I mean, but it's always the quality. You mean percentage of how many times the algorithms were successful in identifying a certain disease.
How many percent?
Yeah, exactly. Yeah, it's above 90. I mean, above 90%.
For cardiovascular, for Alzheimer, for Parkinson, for analysis from the image.
This 90% is what we are working, but I think that it has to be about this same number in any other area, otherwise the doctors wouldn't like this. 95%. If this is even more than 90,
it's possible to obtain this result?
It's possible. I'm absolutely sure that it's possible. I mean, if you have a lot of data, it's possible to get this. I mean, we don't compare with in such way the medical doctors, and I agree with them. And these are the standards for the scientific community, that we would like to go beyond what the medical doctors can do. If they can do 70% and we can do 85%, then this is a success.
Okay.
The idea is to do this better than a higher percentage.
It is possible to prepare the report doctor for medicine directly your algorithm in Python or in which language?
They don't want to know the algorithms. They want to have a front front end to press one button to put the image and then to get the answer. I mean, this is what they want. But in this case, when I was talking about the...
You apply this algorithm after if you know the images. Yes. It's possible to apply directly analysis of pattern from the speech, from the writing.
If you speak, yeah, there is a lot of studies. I didn't work this, but there are a lot of other studies to extract, principally for Parkinson, to extract this information not from images, but from writing, speaking, a lot of other type of data.
In the world exists the application of deep learning directly from the analysis of patterns, from the speech.
The study that I have shown you with the cancer, skin cancer, it's a very, very helpful. I mean, you know, in the universities, we don't do final products that have to be solved. We do proof of concepts. So, and in the university, for example, this with skin cancer, the idea is everybody has the application on its mobile phone. I have some spot that makes me worry. I make this photo, send to the cloud. My algorithm in the cloud is going to decide if the doctor has to look at it or not, and then the doctor will eventually, if the algorithm says it's 100% skin cancer, then it will be faster to.
Thank you. There was another question. Please introduce yourself.
Can I ask about the topic of skin cancer presentation? What framework is better to use, PyTorch or TensorFlow?
I use TensorFlow. I'm better with TensorFlow, but I know that PyTorch is also a good
Is there any
alternative.
significant difference between these two in our case? So which one we should use?
TensorFlow is more easy to use. PyTorch, I find it more complex. I mean, it's more for people that understand good programming. TensorFlow is more. Keras is even better. Go for Keras. Exactly. For more, for better softwares. I can speak to you later.
Okay. Any other questions, please?
Okay, well, I have one question, what is the data set length that you're using for training?
Data?
Data set length. What is the number of data samples that you're using? So because you said that you have 95 patients, but how many images for them you're using?
Did I say 95 patients?
90 something.
No, it was the percentage of accuracy, not patient, not
okay.
patient.
What is
No, the images are, for example, about 10,000 images, 15,000 images.
And in the, let's say for this case, are you using the 120?
The simplest.
This was the simplest,
The
because,
simplest, yes.
okay, I will tell you one thing, if you reduce the neuron numbers, the layer numbers, you have better results. There is this problem, let's say if you remember this formula called the OIA formula for one hidden layer, that is telling the optimal number, that is giving the optimal number of
I will be very honest with you, we use pre-trained model.
Yes, but if you use pre-trained model with lesser number of hidden layers, you have better results, because this
I will send you
model...
the diploma work of my students. It didn't work. It didn't work. I agree with you theoretically, but we tried, it didn't work. So when we use a pre-trained model from Google, it worked better. Sorry. Sorry.
Okay, Professor.
My question is not exactly related to the lecture, but more or less to the neural networks. And you gently touched this problem when you said that neural networks do not model the thinking, the consciousness. And you said really they model the information flow, information process. So do you think that neural networks, kind of neural networks, could be developed on the way, this is maybe future, to model the thinking? What about the thinking? Because you know, artificial intelligence starts with classical artificial intelligence, deep learning, and now they're talking about biological.
If we understand the mechanism of how this happened in our head, probably we can do reverse engineering, but we don't understand how this happened.
What is your opinion? Would neural networks use
we don't need this. We don't need this. We don't need it.
Okay, thank you.
Okay, any other questions?
Probably in the coffee break, because we have a second.
Thank you again. Second speaker of our panel, and he doesn't need actually introduction and representation, but let me say some words about him. This is Professor, Doctor of Science, Petkov, who is also corresponding member of the Bulgarian Academy of Sciences. Professor Petkov also graduated from Technical University of Sofia, formerly VEMI Sofia. He defended his PhD thesis there and Doctor of Science dissertation in the areas of control systems and numerical methods applied to control systems. He is recognized, highly recognized specialist in the areas of systems and control. His results are in the area of developing new methods numerical algorithms and software development in the area of analysis and design of control systems. He is author and co-author of more than 300 publications, for which 4 monographs which are published abroad, 7 books and monographs published in Bulgaria, and more than 200 papers in internationally recognized journals and international conferences. His areas of scientific interest are in the in control systems, analysis and design control systems, as well and numerical methods applied to control systems. Since 1980s, he is member of technical committees of the International Federation of Automatic Control, a member of working groups in the areas of numerical methods and analysis and design of control systems, and he is also member of 4 editor boards of international journals in control. So, after this short introduction, let me present the topic which he is going to represent right now. It's entitled Matrices Depending on Parameters. So, Professor Petkov.
Dear Mr. Rakov, dear colleagues, I want first to express my gratitude to the programming committee who accepted my proposition for this lecture. The lecture is devoted to matrices depending on parameters. The theory of this lecture is developed by the Russian mathematician Vladimir Arnold, and actually it is a part of the so-called singularity theory in mathematics. Another branch of singularity theory is the so-called catastrophe theory, which is well known, and further on I shall try to show some examples of such matrix catastrophes. This is the contents of the lecture. First, we have to consider the geometry of matrix space. Then I shall present the so-called bifurcation diagrams for a small number of parameters. Then we shall consider the so-called stratification of Jordan bundles. And finally, if we have enough time, I want to say something about the finding of the Jordan canonical form as an ill-posed problem. The subject is rather mathematical, but I shall try to explain the theory in popular terms so that I hope it will be acceptable for the people here. We shall investigate in this lecture 2 interesting mathematical objects. They are called manifolds. The first object is the so-called orbit of a given matrix A. This is actually the set of all matrices which are similar to the given matrix A. This means that we are interested in matrices in the form PA, P inverse, for P, which is a non-singular matrix. The set of these matrices is very interesting because it is related to some important properties of the matrix A. For instance, it's related to the Jordan form. As we know, the eigenvalues of the matrix A and the Jordan form of this matrix remain unchanged under similarity transformations of the matrix A. Apart from the bundle, we shall consider, apart from the notion of orbit, we shall consider the notion of the so-called bundle of matrices, which is something like union of all orbits of the matrix A. I shall give later on some examples to explain these notions. And this is an example of manifolds in the three-dimensional space, which are generated by a quadratic equation shapes for different values of the constant C. Now we will see what is the difference between orbit and bundle. Here we have two matrices which have the same Jordan forms. We see that we have one Jordan block of dimension 2 by 2 and two scalar Jordan blocks of dimension 1 by 1. So the Jordan forms are equal, but the eigenvalues of these matrices are totally different. So these matrices corresponds to different orbits, but these two matrices, J1 and J2, they are in the same bundle because the Jordan form is the same. So this is the difference between orbit and bundle. Further on we shall use more frequently the notion of bundle. Now we have to introduce two important notions related to orbit and bundles. These are the so-called tangent space of manifold and normal space of the same manifold. These notions are illustrated here, and we see here this is the tangent space which contains all tangent vectors at the point X, and here with yellow we show the orbit of the matrix A. With red arrow we show the so-called normal space. So we have the tangent space here as a plane, and the normal space in the three-dimensional space is actually a line. This is a one-dimensional subspace. Now we come to the important notion of the dimension of manifold, and especially dimension of orbit and bundle. The dimension of orbit or bundle, this is the dimension of the tangent space. However, in this lecture we shall use more frequently the notion of codimension, and from the equation of the relationship between tangent space and normal space here, we have that the direct sum of these subspaces actually is equal to the whole ambient space. So if this is the tangent space, the dimension of the normal space will be equal to the dimension of the whole space minus the dimension of the tangent space. So we shall use further on the notion of codimension of orbit or bundle, and this codimension is equal actually to the dimension of the normal space. Here we see two actually manifolds here with the thick curves here, and we see their tangent spaces which are of dimension 1. These are scalar tangent spaces shown as lines, and these tangent spaces of both manifolds, they form actually a subspace which is of dimension 2. This is a plane. So we say that in such case these manifolds are transverse to each other, because if we combine the tangent spaces of both manifolds, we will obtain a subspace of greater dimension. Now we have some examples of this notion of transversality, which is very important further on. In this example, we have two planes which are transverse to each other. Here we have additional examples of subspaces which are transverse, and we see that there is something similar between the notions of transversality and the notion of linear independence in linear vector spaces. Here, however, we see two examples of bundles which are not transverse. This is because this intersection of two lines do not generate the 3D space. And here we have actually that the second manifold here with blue color is actually a tangent space to the first manifold. So these two manifolds are not transverse. Now we want to determine the dimensions of orbit and bundles. I'm skipping some mathematical derivations and want to show only this important formula which gives the codimension of matrix orbit. These parameters here, S1i, S2i, and so on, these are the dimensions of the Jordan blocks which correspond to a given eigenvalue lambda I. So, using this simple formula, it is easy to find the codimension of the orbit, and the dimension of the bundle is determined from the dimension of the orbit minus the number of distinct eigenvalues of the matrix A. So I'm finishing with the introduction of the mathematical notions. Now let's see some examples. The first example here, this is the matrix J1, which is which consists of two Jordan blocks. These Jordan blocks are of dimension of order 1, and we have the case of distinct eigenvalues here. Here we may compute the dimension of the orbit and bundle, and we see that using this formula shown in the previous slide, the codimension of this bundle is equal to 0. This is a very important number here. The second example gives a Jordan block of dimension 2 by 2. And here, using the formula, we find that the codimension of the bundle in which is this matrix is equal to 1. And finally, we have the case of two Jordan blocks. These are scalar Jordan blocks of dimension of order 1, but here we have equal eigenvalues. This is a very rare case in practice. Here the codimension of this bundle is equal to 3. Now we may have the following conclusion. This is the most typical case in practice. If you take a matrix at random, you will find that its eigenvalues are different. So here the codimension is equal to 0. This case is very rare, and the probability to find such a matrix in the set of random matrices is actually equal to 0. Here the codimension is equal to 3, the most higher value among these dimensions. Now some examples of orbits and bundles. Here we consider the orbits of 2 by 2 matrices. This was actually the matrix J2, which was single Jordan blocks with eigenvalue mu1, and here the orbits are actually planes in the 3D space, and these planes they are obtained for different eigenvalues, because in the case of orbit, the eigenvalue is important. But all these orbits, they lie in one bundle, because they correspond to a given Jordan form. Actually, a Jordan block of dimension 2 by 2. Now we are going to consider 3 by 3 matrices, and here the most generic case, the most typical case, this is the case of 3 distinct eigenvalues. We have 3 Jordan blocks with different eigenvalues, and this is the most typical case in practice. Here again we find that the codimension of the bundle is equal to 0. Now, this is the most rare case. We have 3 eigenvalues. We have the case of multiple eigenvalues, but these eigenvalues are equal. It is very difficult to find such matrix in the set of random matrices, and we see that the codimension of the bundle in which this matrix is laying, this codimension is equal to A. So, with the increasing of codimension of the bundle, we see that we are going to the least generic case. And actually the first matrix here corresponds to the most generic case, the case which is maybe actually we may have such example very frequently in practice. Now we have a bundle of orbits of 3 by 3 matrices for the case when we has actually 3 equal eigenvalues, which are in 3 Jordan blocks of order 1. And in this case we see that actually we have the unit matrix here, which is multiplied by the eigenvalue mu1. So the orbits here represent points in the 3D space, and these points correspond to different matrices, which are actually the unit 3 by 3 matrix multiplied by the corresponding eigenvalues. And these points, they are lying on a line, and this line is the bundle, in the bundle in which these orbits are participating. Now we may make some conclusions. In the general case of n Jordan blocks, we see that the most generic case, this is the case of n distinct eigenvalues, and the codimension of the bundle is equal to 0. Here we have some intermediate case, and here we have the most degenerate case, in which the codimension is equal to n squared minus 1. So the codimension of the bundle of matrices is giving us very important information. This information is about the property of this matrix. It may be in the most generic case, but it may present the most degenerate case. Now, until this moment, we were in the space of matrices. Now we are going in the space of parameters, which determine a family of matrices. If these parameters change, we obtain a family of matrices, and for small changes, we speak about the so-called deformations. So a matrix family here is defined in mathematical way as a mapping from the parameter space to the space of matrices. And here we have an important picture which shows what is happening when the parameters of the matrix change. Here with the thick black line we show a family of matrices, and this family actually consists of matrices which have distinct eigenvalues. In some sense, this is the most generic case. This is the most typical case, matrices with distinct eigenvalues. However, at some point, which is called singular point, we cross the manifold of singular cases, and this manifold consists of all possible Jordan forms for this number of parameters. And when the matrix family is crossing the manifold of singular cases, the eigenvalues change with jump, and from distinct eigenvalues we are going to a case of some or all multiple eigenvalues. Actually, if we are on the manifold of singular cases, we will have the case of some Jordan form. The eigenvalues will participate in a Jordan form. Now we shall consider what is happening in the space of parameters. Actually, in this space we may consider also bundles, which corresponds to the bundles in the matrix space. I shall illustrate this with some examples. Here we have the case of 3 parameters, and in the 3D space, the manifold of singular cases correspond to this conus. And here we have the case of Jordan block of order 2. Here we have 2 Jordan blocks of order 1. And here, outside the conus, we have the case of different, distinct eigenvalues. So almost all the space is full of matrices with distinct eigenvalues, but on some surface, this is the conus, we may have Jordan block of order 2 or even 2 Jordan blocks of order 1. Actually, this is the most degenerate case, and of course this case here is the most generic one. The next example is an example of the Jordan form, but this is apart from the next picture. Here we have the case of 2 Jordan blocks. The first Jordan blocks of dimension 3 and the second Jordan blocks of dimension 2. The first Jordan block have eigenvalue alpha, and the second Jordan block has eigenvalue beta. And here we say what is happening in the space of, in the parameter space. Here we have again 3 parameters, and if these parameters change, we may have the case of distinct eigenvalues. This is the most generic case. Almost the whole space is full of such matrices with distinct eigenvalues. But on some surfaces, we see that we may have the case of 1 Jordan block of dimension 2. Here we have Jordan block of dimension 2 and Jordan block of dimension, and another Jordan block with eigenvalue beta of dimension 2, and so on. Next, we consider probably the most complicated case. Here we consider a Jordan block of dimension 4 with eigenvalue alpha, and we see that here we have 4 Jordan blocks of order 1, but with distinct eigenvalues. This is the most generic case. Almost the whole space is full of such matrices. But on some surfaces and curves, we see that we may have different Jordan blocks, combination of different Jordan blocks. And the most degenerate case, this is the case of Jordan block of dimension 4. And this is actually this green point here. So the most generic case, this is the case of 4 different distinct eigenvalues, and this is the most degenerate case. The other cases are in the intermediate between these 2 important cases. By the way, this picture illustrates the difficulty in finding the Jordan form of a matrix, because in the space of parameters, we must find this point here. where we have a Jordan block of dimension 4. And this is very difficult in the presence of model errors, rounding errors, and so on. So this theory of matrices depending on parameters is closely related to the numerical problem of finding the Jordan form of a matrix. Here we consider the particular cases related to the previous picture. This is not so important, but again we have here the most degenerate case. Its codimension is equal to 3, and the most generic case, this is the case of codimension equal to 0. So, if we determine the codimension of the matrix, and this may be done relatively easily from the given matrix, it is possible to say immediately what is the structure of the Jordan form corresponding to this matrix. This is the final case of 3 Jordan blocks of dimension 2, which are associated with eigenvalues alpha, beta, gamma, and these codimensions, these bundles here have codimension equal to 1, which corresponds to planes in the 3D space. Now we may order the possible Jordan forms in this using this graph, and here this is done for matrices of dimension of order 3 for 3 by 3 matrices. Here is the most typical, the most generic case of 3 different distinct eigenvalues, and here is the most degenerate case of actually 3 Jordan blocks with the same eigenvalues. And the rest possible Jordan forms, they lie between these 2 cases. So it is interesting that for a given matrix we may have such stratification of the possible Jordan forms, and this is important from numerical point of view when we may find numerically for instance, this matrix, but we may decide that actually we may have this matrix here, this Jordan form, as the true Jordan form of the matrix, but this Jordan form is obtained due to the rounding errors during the computations. Here we show what is happening in the parameter space. This is very interesting from numerical point of view, and if we have a matrix which is near to the surface of singular cases, this surface contains all possible Jordan forms. With approaching the surface of singular cases, the conditioning of the problem is worsening. I mean the eigenvalue problem, which it has to be solved. And it is interesting that if we are very near to the surface of singular cases, the conditioning of the problem is extremely worse. But once we are laying on the surface of the singular cases, then the sensitivity of the problem is normal, not so high. This is very interesting from numerical point of view, and this gives actually an idea how to find the Jordan form of a matrix. In practice, we have the matrix A, which is in some sense the true matrix, but due to model errors and rounding errors, we have the matrix A tiled, and these matrices are in different bundles. If the matrix A is lying on this bundle, actually the matrix A tiled is lying on another bundle. And now we are projecting the eigenvalue problem, which corresponds to the matrix A tiled, to the point with matrix A hat. And actually this is the Jordan form, the numerical Jordan form, which may be found during the computations. And here we have the distance between the true matrix and the matrix which is corresponds to the Jordan form computed with the corresponding algorithm. So this is the case. Actually, finally, we are going to the same picture we had previously of k-parameter family. Actually, in finding the Jordan form, now we are finding a Jordan form which corresponds to a ball of parameters. So this is not a singular point, but actually this is a ball of parameters. And for all parameters inside the ball, we have the same numerical Jordan form. This guarantees that this Jordan form is robust to the changes of the parameters. And finally, this is the actually a small excerpt of literature about the problem. The literature is very rich, but with this I'm finishing. Thank you very much for your attention.
I'm opening the panel for questions. Do you have questions? Asperu.
I didn't get enough understanding about how in practice we decide what is the most promising bundle when projecting the A-tile over its so-called true bundle. That, because we have to have a priori information about that.
Well, the a priori information consists in two thresholds which are using in finding the sets of multiple eigenvalues, the so-called numerically multiple eigenvalues. So this threshold is actually equal to the uncertainty in the matrix A, and we must know the level of this uncertainty. So this threshold in practice is taken to say 10 to minus 6 if we expect that if we know actually if the uncertainty in the matrix A is of order 10 to minus 6. And we have an additional threshold which is used in finding the Jordan form, because in the numerical finding of the Jordan form we neglect some small singular values, and we must use another threshold for finding the number of actually non-zero singular values, which is the numerical rank of the corresponding matrix. But these are details of the algorithm for finding the Jordan form.
But it depends on the machine precision.
It depends on the machine precision, this is true, but it depends very much on these tolerances, on these thresholds. You must know what is the uncertainty in order to find the best approximation, which is very near to the original matrix A. We must we must actually determine this distance. This is the backward error in finding the Jordan form, and this distance should be sufficiently small in order to accept the matrix A hat as a good approximation of our problem.
Thank you.
Thanks.
Okay. Other questions, Petia?
Thank you for your very interesting presentation. I'm not working in this area, but I would like to ask you, can we apply the same theory for 3D matrices, or it's only valid for n by n matrices, only valid for squared, two-dimensional matrices?
Actually, this theory is applicable to many problems, not only to this problem here. The problem here is actually to find the numerical Jordan form of a matrix. And because I'm working on this problem now, the lecture was oriented toward this problem. But actually this theory may be used for many other problems. You must find actually the equation for the orbit. This equation is linearized to find the tangent space, and when you have the tangent space, you may determine the dimension of this time and space, and this actually gives the co-dimension of the corresponding bundle.
It has to be always applied for square matrices, n by n.
Yes, here it is applied for square matrix, but you may apply this theory for rectangular matrix if you consider, for instance, the linear least square problem or the problem for finding the numerical rank. You have the same actually statement of the problem
For n by n matrix.
for n by n matrix. The theory is universal. Actually, this theory includes many other things. In the original paper of Arnold, you will find the so-called method for determining the normal forms of matrices, and this is much more complicated and interesting, but this is only introduction to the problem.
You mentioned also orbit of matrix means similar matrices.
The set of all similar matrices.
How do you quantify similarity?
Similarity is quantified by this equation here, which was given at the beginning. I shall find it now. Here is the equation of an orbit. Here P is an arbitrary matrix, but this matrix should be non-singular matrix. And if you change P, you find another matrix. And for infinity number of matrices P, you will find a set which is actually the orbit of the matrix A. Of course, the notion of orbit is much more wide than the sense which we use here, because orbit is a notion in the theory of dynamical systems related to the trajectories of dynamical systems. But the singularity theory actually is dealing with the theory of dynamical systems, and this case here, the matrix case, is in some sense the simple case of the singularity theory.
Okay, other questions? Well, I have.
I would like to ask, does it apply also to characteristic functions, like eigenvalues of transfer function matrices?
Yes, it should be possible, yes.
There are some Riemann surfaces also.
Because you have matrix, but you must define in the corresponding way the orbit of the matrix. And once you have the orbit, the equation for the orbit, then you may use this theory without problems.
Okay, I have one question. How do you compute the projection? The projection P?
You mean in finding the Jordan for the
Yes.
Now, of course, I skipped many details due to the lack of time, but we have the corresponding picture here. Here the problem which we consider is actually a regularization problem. We have ill-posed problem because the case of multiple eigenvalues is actually a singular case, and the problem for finding multiple eigenvalues is an ill-posed problem. And this problem should be regularized in order to find a solution which has some sense. And this is done by this projection here from a tail to a head. And in this projection is done by using the singular values of some matrix. We determine the singular values and we neglect these singular values which are smaller than some tolerance. And actually this is the projection on the corresponding bundle. Because the number of the singular values corresponds to the bundle in which the approximation A lies.
Okay, and just to in some
shall
sense to
miss the
understand,
content.
just a small question. When we have this, the manifold, the bifurcation manifold, I understand it is bifurcation point. When we have from one case, from one quality to another.
This is a catastrophe, this is a matrix catastrophe.
Okay, is it possible to relate this bifurcation somehow to the dimension of the eigenspace of the matrix? Because in the first case, different eigenvalues, we have n-dimensional eigenspace.
Yes.
Then we have Jordan form, which reduces the dimension. We have generalized. And then we again have, like the identity matrix, we have again return to the initial level.
This is just what we are doing. Actually, we are considering here different Jordan forms which correspond to different dimensions of eigenspaces. So here we have the case of 4 distinct eigenvalues, but here we have actually one eigenvalue and the Jordan block of dimension 4. Actually, you may find what is the difference between these eigenspaces. And actually, these bundles, they correspond to different eigenspaces.
Okay, any other questions? Okay, let's thank Professor Petkov.
Thank you.